Yeah, so I'm Chris. Let's talk about what this talk is all about. So honestly, mainly I'm a little bit embarrassed about something that we did at work. But therapy is expensive and they usually don't put out free pizza and beer, so I opted to talk about it here instead. So I work for a company called Unison. It is a brand new programming language and it is based around distributed programming. So we have lots of weird and new problems that we're trying to solve all the time. But let's dig right into the most embarrassing one. So we were building a new feature, which is a code hosting platform. So normally you would just use GitHub for this, but Unison, because we do things a little bit differently, we actually don't store code as text. You write code as text, and then you check it in, it compiles and type checks, and then it dumps it in a serialized format into a SQLite database. Turns out, GitHub does not love diffing SQLite databases. So we need our own custom code hosting platform. Okay, great, that's awesome. We can really integrate this into our language and provide a good experience. We definitely want to do that. This is sort of what we were imagining. So in reality, this is, spoilers, this is exactly what we built. It's easier to do these talks in the future. And so you can see, you know, we've got our code that you can walk through on the left, and we've got our source printed out there, and we've got our documentation. You can click around and view stuff and whatever, right? So great experience, you know, better than a binary diff of a SQLite database, I'm sure you'll all agree. So we wanted to build that. Okay, why did we want to build this thing? Well, we had a fundraising deadline coming up. We're a venture capital funded programming language, so we actually have investors, and we need to provide some value to those investors to convince them that, like, we're not just a bunch of nerds building a computer language for fun, even though that is what we are, don't tell them. But we can convince them that maybe someday somebody will pay money for it, it helps a lot. So we were like, okay, we gotta build this feature, we've got 2 months to do it before our next fundraising deadline, and if we can build something that shows this potential, they'll invest more money. But we had a problem, which was that all of our code was based on the kind of, you know, laptop local development experience. We had no web app, we had no web server. All of the code was based on this SQLite local application model, right? And we needed to ramp up a web app and build a whole new online system in 2 months. So we thought about what we would need to do in order to accomplish this. The advice from the internet, of course, is never, ever, ever, ever use SQLite on the server. You Google this, you check on Stack Overflow, that's not what it's built for. What are you doing, you maniac? Okay, so we had some options about what we could do in order to interact with our weird serialized code on this backend server, right? Okay, first option, screw them, use SQLite on the server anyway, right? Another option, try to rewrite with Postgres. I used the word rewrite on purpose. We all know how rewrites go. It was, in my estimation, would take 6 months rather than 2, and would probably be slower, worse, and unfinished at the end of that. So our third option is just do nothing, say, hey, investors, believe in us, I guess. And, you know, that would maybe work, but we really wanted to present something. So when I look at this list, I really do only see one option. So we use SQLite on the server, right? Okay, damn Stack Overflow, we're doing it anyway. And it worked great. It works great. It does still work great. It's been a couple months that it's been live. You saw the image. I served that from my web browser, clearly working. We had consistent usage and everything is going great, and we actually landed the funding that we needed. So, great, all right, all's well that ends well, thanks for coming. That's how you solve the exact problem that I had. But I wasn't super happy about this. Okay, why wasn't I happy? Well, wasn't this a hack? Like, we had one rule, don't use SQLite on the server, and we broke it. Aren't hacks bad? Was I a bad programmer? Like, I don't know, I solved the problem, didn't I? That's what they pay me for, ostensibly, at least. So I kind of was at odds here, right? It felt bad to do this thing. The thing was right because it worked. How do we reckon with that? So I started thinking, like, okay, what actually is a hack, right? I felt like this was a hack. Are they actually bad? Like, what constitutes something that's hacky? And like, it kind of feels like that's one of those you know it when you see it things. So here's my personal definition at the time, right? And it's like, okay, we're solving a problem by doing something sketchy. Okay, well, what's sketchy? Like, this means nothing, right? A lot of us have just this intuitive understanding of what we think hacky is, and that hacky code is bad. But what is a real description of a hack? And I would challenge you to sit down and try and write one out, and it's probably going to end up something like this. Maybe it's code that's not elegant. Maybe it's code that's hard to read. Maybe it's code that's not idiomatic, right? We're doing it some different way than most people like to do it. But the reality is, these definitions are super imprecise, and they're like not super useful. So when you describe a problem or a solution as hacky, you're just left wanting. Like, what do you do? What do you do from that point on? If there's something actually wrong with the solution, you need to say so, and you need to say so specifically so that it's actionable, right? Saying it's hacky is a cover your ass statement because you know something is wrong, but you don't know what. So in this particular case, I would say we just got lucky. We had one option, we took it, and it worked. I would rather not base all of my future choices on luck. I don't want to flip a coin and say, well, do we do this or do we do that? And if it works, I still have a job, and if not, well, we're out looking. So what can we actually take from this one successful experience that's repeatable and that we can apply to all future problems? And really, that just means, like, how do we learn the skill of problem solving? This talk was originally just going to be like how to design a good hack. Like, we did a thing that I thought was bad. How do I convince you all that it was actually really great? But I think this is a kind of a contradictory statement, like a good hack, because you only have a hack if you don't understand what's happening and you can't justify the decisions you made to get there. That's the difference between a hack and a solution, is that you understand the choices you made on the way to a solution, and a hack is something you just did because you had to or because it worked. So that leads us to, how do we design a solution rather than a hack? And how do we design that from first principles? And if we do it this way, we can actually write in that description of that PR, this is why I did it, and that makes it not a hack. Okay, so how do we actually learn how to do this? Let's learn from some skilled problem solvers, right? Rather than just trying to get lucky. So this really clicked for me when I was watching a YouTube video from Martin Mullen, whom you may not be familiar with, but maybe this will jog your memory a little bit. There was a viral video going around a little while ago. He designed this giant mechanical marble-based music machine. It's really cool. You should definitely go check it out. And along the way, it turns out he's the first person to design a machine of that scale, go figure. And he had to solve just all sorts of weird problems. And something that they all had in common was that nobody had solved these problems before, and there wasn't like a set list of, okay, you do this, you do that, you do that. You have to design an innovative solution. And so he came up with his distillation of the first principle design philosophy. He didn't invent the philosophy, but this is how he explained it. There's two steps. The first step is you need to question your assumptions and find the fundamental truths. And I mean all assumptions here. We're going to look at some case studies in a little bit that show that, like, you need to question everything, all the way down to the bottom. And the second part of the solution is, okay, now you've questioned everything, just rethink your solutions from scratch. And that sounds really glib, but this is really just like a guiding principle, right? This will give you better solutions if you do it this way. You still need to have some problem solving skills. But hopefully this should apply to basically any domain. So I've added two additional clarifying questions here. One of them is that we need to find the actual goal, okay? And we want to be wary of this XY problem, which, if you haven't heard of before, the XY problem is the idea that someone is asking a question which is focused or predicated upon a specific solution, namely Y, and rather than the problem itself, the root cause, or the thing that they really need to solve, which is X. So they've already zeroed in on a particular solution and you're asking questions about how to do that, but you need to question that, back up, and find out if there are other paths that you're not thinking about. So here are some examples. These are straight off of the Wikipedia page for the XY problem. This is a known thing. And someone on Stack Overflow might ask, how do I get the last 3 characters of a file name? Okay, perfectly cromulent question, like you can answer that. People do. They say, oh, you pipe it through tail and you do this crazy command and you will successfully get the last 3 characters of a file name. But that's not what the user wanted, even though that's what they asked. What they wanted was, how do I get the file extension of a file, right? And this is a much more general thing, but it turns out, even though this seems like a harder problem, someone already solved that problem, right? And there are Unix utilities, right? Base name or dir name or whatever you need to get this answer. And so if you ask this question instead, you get a better answer because it's all already done for you and it works for file extensions that aren't just 3 characters long. Okay, another quick example. Someone asks, how do I get the string between these 2 curly brackets, right? Again, perfectly good question. They've already started going down this solution when really what they want to do is get a specific value from deep inside a JSON string. Well, you should parse the JSON, and your library probably has something to do that for you. So basically, we need to be very careful about the problems that we're asking to make sure that we haven't already started down the wrong path. Okay? The next clarifying question we can ask are, what are my hard constraints? Things that can't be compromised or that I need to consider in my solution space. So for us, in our particular case, we had a hard constraint, and that was time. We had 2 months until these investors were going to look at what we had, and we needed to work within that, right? But there's other constraints you can consider, money, and I'll bring up at this point that you can also consider which things are not constraints. So in certain cases, we did this actually a lot when I worked at Vendasta, we would recognize that we had money for a specific problem, and you throw a few $1,000s at that problem and it goes away. And then you move on with your life, right? And so if you recognize that, hey, actually like money is not a constraint here, or performance is not a constraint here, you can really rip through a lot of problems really quickly. So write these things down. Correctness. This also might sound a little silly. Not all problems need to be solved in a correct manner. If you work in a business setting and you can do something that nobody else can do to 90% correct, and someone else just kind of has to come and clean up the rest, or like, you know, you do it 90 and the current solutions give 0, that's still a huge offering. It doesn't necessarily need to be 100% correct. If you're working for a bank in the medical field, yeah, maybe. But notice what is your constraint and what isn't. Okay, so let's look at some case studies here. So we're going to learn from a different Martin now, Lockheed Martin, namely, and their Skunkworks division. So their Skunkworks division, this is a weapons manufacturer, and they had a division for aircraft design. And this was like a very experimental, advanced development projects, completely separate division. They had their own management, they could do their own organization, and it was for very secret or advanced missions. So they had to solve some crazy problems that nobody had ever done before, and maybe nobody was even allowed to hear about. Okay. So a lot of the stuff from this section is taken from this talk, which you should absolutely check out. It's from RailsConf a long time ago, and Nicholas Means goes through a lot of these next 3 case studies in much greater detail, and you should absolutely check out this talk. It's phenomenal. And if you're interested in aircraft, he knows a lot more about them than I do. But we're going to look at them from a different perspective, which is this problem-solving perspective. He looks at them from like a project management perspective. So, the Air Force goes to Skunkworks, and they say, here's our goal. We want to design a plane that can fly behind enemy lines without getting caught on radar. Okay, they want a reconnaissance plane, they want to take some photos over the USSR, and they want to do that without losing any pilots, and they need to get those pictures back. Okay. Skunkworks are experts at questioning assumptions. They question an assumption in designing this plane, which nobody had ever designed before, which was the assumption that reconnaissance planes should probably be fast. Okay, what if we look at this from a different perspective and the plane doesn't need to be fast? Is there a different way we can solve this? They question another assumption, which is that planes should be able to land. Yeah, we'll see how that works. And this just really drives home, you need to go back to basics and forget everything you knew. So what did they design? They came up with this. We have a photo, so you know it worked, and they built at least one. No, they built many. This is the U-2 Dragon Lady. It was a reconnaissance plane from the 1950s. It flew higher than any plane had ever flown at the time, up to 70,000 feet, which they thought was higher than the USSR radar could see. So the goal was, if we can fly above radar, we don't need to be fast. We can take our time, we can get the photos, and we can get out. We'll be invisible. And in order to achieve this goal, they needed to cut as much weight as they possibly could. So you'll notice in that image, the landing gear, what's different? They have 2 sets of landing gear rather than the traditional tripod of 3. And they're right in line, kind of like a bicycle. Okay, think about that for more than 10 seconds, and there's some implications. When you're taking off, they actually needed to wheel out additional wheels, one under each wing, and they would taxi down the runway, take off, ditch the extra wheels because they didn't want that weight. But now you're coming back after your mission and you need to land. Okay, what do? Well, you get as close to the runway as you can, you have a chase car come in behind you with another U-2 pilot who knows what they're doing. These planes were designed to fly as high as they possibly could, so they generate massive amounts of lift from those wings. They physically cannot land on the runway because they have an air cushion under the wings that prevent it. So you get down as close as you possibly can to like 5 feet above the runway, 4 feet above the runway. You can make it to 3 feet. You stall the plane, and then you drop that 2 feet onto the runway. Okay, but you're still just on 2 wheels. So the pilot does the best they possibly can to balance the plane and slow it down as much as possible, and then you just skid to a stop on your wings. And that's how they landed this thing, because this is for special missions, right? You don't need a quick turnaround time. It's okay if it takes damage, you can repair it in between missions. It got back with the photos intact. It doesn't matter if it lands funny. Okay, so there was a flawed assumption in this original goal. I don't know if you caught it. I told you the goal was to design a plane that can fly behind enemy lines without getting caught on radar. This plane got caught on radar. They thought that 70,000 feet was high enough to be above the USSR radar. They were wrong. And they got caught on radar, but none of the enemy MiGs could fly high enough to actually shoot them down. So I'm sure they had some very stressed pilots, but they made it back in one piece. So it turns out they did not need to avoid getting caught on radar if they could just fly high enough that no one could catch them. Okay. So a couple years down the line, the Air Force comes back to them with another problem. They say, we need you to design a plane that can fly behind enemy lines. We've learned our lesson this time. It just needs to not get shot down. They could see the end of the impending end of use for the U-2 because surface-to-air missiles technology was getting better, and technology ever moving forwards, all that jazz. So they needed a new design, and they wanted to get on top of this early. So Scout Corps sat down and they thought about it. They came up with a new potential solution this time. They said, well, what if we can just fly faster than the SAM missiles? So they came up with the SR-71 Blackbird, which was introduced in January of 1966. It could fly at Mach 3 at 78,000 feet, which, if you don't know, is very fast. There was only 32 of them ever built, and I don't believe any of them were ever shot down. Building this thing, they had to invent completely new manufacturing techniques because it's, I think, the first plane that was ever constructed out of mostly titanium, and they had to question that assumption too. This thing had a very peculiar design decision at its core. They questioned an assumption. The assumption was that planes shouldn't leak fuel all over the runway. I am not kidding. So, how does this even work? Well, the problem is, when you go Mach 3, that's a lot of air passing over your plane. That plane heats up. Titanium expands. Okay, So if you're designing a fuel tank, you better have room for all of the metal in that tank to expand, or you're gonna have a very bad day. Well, they couldn't figure out a way to design a fuel tank that expanded correctly, so they said, well, we'll build it undersize, it will be leaky at ground level, we will fuel it up just as much as we need to, it will gush fuel all over the runway, we'll take off, get up to speed, the fuel tank will heat up and seal, then we'll top up in midair and go fly the mission. It's insane, it's genius, and it worked. So, the Air Force comes back to them again, a couple of years later. Same problem, now they have an additional constraint. Now we need a payload. So, we need a new solution. We can't fly high because we need to carry a bomb. We can't go too fast because we need to aim a bomb. What do? We're going to question an assumption that planes should be aerodynamic. Again, I would have thought that planes should be aerodynamic. That's why I don't work for snowbirds. They built this. I'm sure you've seen one of these before. This is the F-117 Nighthawk. It came out in around 1973. And they decided, hey, we don't need to be fast or fly high if we are just invisible. Now, the assumption that they questioned was that you needed to be aerodynamic. This thing is literally unstable in all three possible axes of flight, and apparently it was damn near impossible to fly this thing. But they didn't have to go fast. They hopefully didn't need to do any evasive maneuvers because they designed it to be invisible. Weird fun fact, this angular design with all the sharp corners, you don't need to design a plane that way in order to be invisible to radar. But this made it much simpler for their software to construct a design that was radar invisible, and they just simply didn't have the computing time to do this with curved edges at the time. So they can do better now, but this is what they had to work with, and they made it work. And this thing was more invisible than the radar test pole that they mounted it on in order to do the tests. The radar engineer could not see this on the field. So that's Skunk Works. Clearly very successful, and they got there by questioning some pretty wild assumptions. Let's take a look at just a couple software designs that do a similar thing. One goal here is that we might want to make an app run as fast as possible. I think we've all encountered this at some point. We can question some assumptions. And depending on your use case, we might say, well, what if my app just leaks memory all over the floor? Right? We've learned something from the Blackbird. Sometimes leaking is okay. And it turns out that depending on your application use case, if you are designing a linter or a compiler or a checker, you need that to run on every user key press. You need it to run as fast as possible, and then it shuts down. So why are we going to be concerned about freeing and managing memory when the operating system is going to need to free all of that memory anyway? So if you use a language like Zig, for instance, it allows you to specify a different memory allocator for your application. You just give it one that always allocates new memory and never cleans anything up. It turns out it's going to be blazing fast. And it's totally fine, and it works great, and a lot of people do this now. One last story. So, this is a Nintendo Game Boy. The goal that Nintendo had when they released this, they had a little design team that needed to prevent the sale of unlicensed video games. They had found, after the release of the NES, that a lot of bootleggers and other companies would reverse engineer the NES, and they would build games for it, and then they would sell them. And it turns out that that wasn't illegal, right? You can release a game for a computer that it'll run, that's fine. There was nothing illegal about releasing a game that would run on the hardware that you have. But Nintendo didn't like it. They didn't get any money from those sales. People were releasing low-quality games, and it made the NES look bad. They needed a solution for this. So for the Game Boy, they said, okay, we're going to try something else. They had some solutions at the time that mostly revolved around kind of these question-answer query chips, but they wanted to go a different direction. And they questioned an assumption to do so. That assumption was that this requires a technical solution. Okay? How can you solve this problem without a technical solution? We need to prevent these games from running. No. They came up with this. I'm sure we've all seen this. In fact, I can guarantee that you've seen this if you've ever played a Game Boy game. And the reason I can do that is because on boot up, when the Game Boy loads a game, it will physically check what is being written to the screen during boot up, and it must display this logo, or the hardware will not boot the game. The reason that they did that is they cannot prevent unlicensed games from being created, and there's no law against selling them, but there is a law against copyright infringement. If you display this in your game, we can sue you for copyright infringement because that's our logo and you are not licensed to use it. So they manufactured the hardware to require you to commit copyright infringement in order to write a bootleg game. Absolutely genius. Okay, so let's recap just a little bit on what we learned today. Advice from the internet is great, but it probably won't apply to your most difficult problems, and that's because internet from the advice lacks nuance, and if you are solving a new problem, by definition, no one on the internet will have the context or have seen it before in order to give you good advice. If you're designing from first principles, you need to question your assumptions, and I mean all of the assumptions. Find those fundamental truths. Then rethink your solutions from scratch. You have to find the actual goal or the problem that you're trying to solve, and you should probably question it 3, 4, 5 times before you think you've actually made it there. And you need to analyze what your hard constraints are, whether that be time, money, legality, performance, really anything, so that you can find which things you can flex and which things absolutely won't move. Great, I'm Chris. Come talk to me after. If you want to talk to me about Unison, if you want to talk to me about aircraft, if you want to talk to me about whatever, just come find me after, and thanks for listening. Appreciate it.